Hello guys, this is day 16 of our daily push-up challenge while solving a problem from Putnam. This one is from Putnam 1941. So this predates this problem predates some World War II. Okay, so let's insert some push-up in there first. 1, 2, 3, 4, 5. Okay, and again, let's write our progress here. And that looks ridiculous. Let's rewrite it. Okay, and then let's read the problem. Assuming that fx is continuous on the interval 0, 1, prove that the integral of x from 0 to x equals 1, integral from y equals x to y equals 1, integral from z equals x to z equals y, of f of x, f of y, f of z, dx, dy, dz equals 1 over 3 factorial of integral of t from 0 to 1 of f of t dt quantity cube. Okay, and yeah, so this looks like a weird notation. Usually in the limits we don't write the variables anymore, and it's understood that when the order of integration is such that the d's are written first on the left and then you proceed to the right. So let's write that in the modern notation. So integral from 0 to 1 of x, integral from x to 1 of y, integral from x to y of z, of f of x, f of y, f of z, and this is the modern notation I'm talking about. So we integrate z first, and then we integrate y, and then we integrate x finally. So that's equal to 1 over 3 factorial, the quantity integral from 0 to 1, f of t dt cube. Okay, so that's the thing that we're trying to prove, is that the left hand side equals the right hand side. 6, 7, 8, 9, 10. Okay, and then let's write that here. So I was thinking, since we'll be integrating a lot of functions of f, I think it would be beneficial to define capital F, which is the integral or the antiderivative of small f. So let's call this, what variables do you have? You have t, so let's call this f of u, okay, is equal to the integral from 0 to u of f of t dt. Okay, so this is just from the fundamental theorem of calculus. This implies that if you take the derivative of f with respect to u, f of prime mu, this is just equal to f of u. Okay, so again, fundamental theorem of calculus. Therefore, right hand side, so we usually write RHS, meaning the right hand side. We can write that as, of course, that is just 1/6 the integral from 0 to 1 of f of t dt, and then this is cube. We can always write that as 1 over 6. So integral from 0 to 1 f of t dt, that is just capital F evaluated at 1, correct? Because your limits here is upper limit is 1, in here your upper limit is u. You evaluate u equals 1, so you have capital F of 1, and of course this whole thing is raised to the power cube. So we want to show that, all right, the moment we end up with 1/6 capital F of 1 cube, then we're done, because this right hand side is just equal to the original expression right here. Okay, so let's proceed. 11, 12, 13, 14, 15. Okay, 15. So what do we do next? Well, let's work on the integrals that we have above, and let's focus first. So let me write this as integral from 0 to 1. So this is integral of x variable. Let's write of f of x here. Integral from x to 1. This is the y variable. So let's write f of y here. And then let's work first. So let me use a blue ink. Let's work first on the z variable. So you're integrating it from x to y of f of z dz. Okay, we work with the blue ink right there. So that's dy dx. Okay, so let's work on the blue, the integral written in blue. Again, using the fundamental theorem of calculus, we know that this is merely equal to capital F, okay, because capital F again is the antiderivative of small f, capital F of y minus capital F of x. That's just the evaluation of the blue integral, okay? And then once again, we write the rest, dy dx, and then you have fy integral from x to 1, and then you have fx integral from 0 to 1. Okay, so now let's work on the y variable. So let's write integral from 0 to 1 f of x, and then the y variable, let's use a green ink. Integral from x to 1 f of y, and then that is note that, so let me already write it here. Note that our small f of y from our definition above is just equal to the derivative of capital F, correct, with respect to y. So therefore, let's write that down here already. This is f prime of y multiplied by capital F of y minus capital F of x, and then dy, and then you have dx. And again, we're integrating with respect to y. So from the point of view of y, all the other variables like x in this case is just a constant. Okay, let's continue the push up. We're now at 15, 16, 17, 18, 19, 20. Okay, so we write that down, 20. Okay, so let's solve the blue integral. So let me make a pro move here. So because you have something of the form f prime, a derivative of a function multiplied by the function itself. We've seen this over and over. We've seen this at least, I think, 2 times already in the previous push-up videos that we have. The moment you have the derivative of a function multiplied by the function itself, you can always turn it into the derivative of that function squared, okay? So the pro move that we're going to do here is we're going to introduce a factor of 1/2, okay, and then we'll have something like 2 times f prime of y, capital F of y minus capital F of x squared dy, okay, and then note that this whole thing, okay, sorry, there's no squared there, it's just f of y minus f of x. This whole thing is equal to the derivative with respect to y of what? Well, that is just f of y minus f of x squared, correct? Because when you get the derivative of this, you got 2 times quantity f of y minus f of x multiplied by the derivative of capital F with respect to y, which is just the term that we underbraced right here above, okay? That's just equal to the whole derivative here below, okay? So then let's copy everything else. So you have 1/2 dy integral from x to y. Well, this is now the integral is now an exact differential. Therefore, the value of the integral is just 1/2 f of y minus f of x squared evaluated from x to 1. Okay. Well, this is just let's copy the rest. F of x integral 0 to 1 dx. Okay, so that's the simplified form. And again, everything in the blue thing, sorry, not blue, the green thing, you can simplify it further. When you evaluate it at y, at 1, you get f of 1 minus f of x squared. However, if you evaluate it at x, you get f of x minus f of x, which is just 0. Okay, so we are left with the integral from 0 to 1 f of x, and then you have 1/2. So we are just left with capital F of 1 minus capital F of x squared, and then you have dx. Okay, so finally we can now proceed with the integration of x. So we write that as the integral from 0 to 1. Again, f of x we write as the integral, the derivative of capital f prime of x. So we write this as f prime of x. Let's write 1/2 outside. 1/2 f of 1 minus f of x squared dx. We're now at 20, so let's finish the push up first. 21, 22, 23, 24, 25. Okay? So we proceed with exactly the same technique that we used when we evaluated the green integral, okay? So the pro move that we can do right here, integral from 0 to 1, is this time we introduce a factor negative 1/3, okay? And you'll see the reason why. That's because we will have here minus 3 f prime of x, f of 1 minus f of x. So we'll see why we needed to introduce a negative 3 because the function inside the square brackets is negative fx. Okay, that's the reason why it has to be negative. Okay, dx. Well, this entire thing, okay, is just equal to the derivative with respect to x of what now? So that is just the derivative of capital F of 1 minus capital F of x cubed. Correct? Because when you take the derivative of this guy with respect to x, that gives you 3 multiplied by the quantity capital F of 1 minus capital F of x squared times the derivative of fx inside, which is just negative f prime of x. So that's why you have minus 3 in there. Okay, and then let's just copy everything else. Let's put negative 1/3 outside the integral. So that gives you a negative 1/6 integral from 0 to 1 dx. Again, the integrand is now an exact differential. So therefore, the evaluation is just negative 1/6 f of 1 minus f of x cubed evaluated from 0 to 1. Okay, look, when you evaluate this at 1, okay, the entire thing gives you 0, correct? So the only thing that gives a contribution is when you evaluate it to 0, because when you evaluate it to 1, you get capital F of 1 minus capital of F of 1. Okay, so when we evaluate it at 0, this lower limit is minus. Okay, when you evaluate it at 0, so therefore this whole thing becomes positive 1/6, and then you have F of 1 minus F of 0 cube. Okay, but recall that F of 0, if you look at our definition here, when you set u equals 0, F of 0, the whole thing becomes 0, correct? Because that's just the integral from 0 to 0. Therefore, this capital F of 0 is just 0, and we are left with 1/6 f1 cube. Okay, and like I said, if the left hand side will become this form, then we're done, because like we said before, this form, which is just this 1/6 capital F of 1 cube, okay, is equivalent to the right hand side, like we've shown here first. Okay, I'm not sure if I did already 25, but just to be safe, let's add it again. 20, 20, 21, 22, 23, 24, 25. Okay, but that's it, guys, for day 26. This is not that long really, but yeah, it's very involved because it uses fundamental theorem of calculus multiple times. Okay, but this has been day 16 of our daily push-up while solving a Putnam problem from 1941. I'll see you guys next time. Thanks for watching, and bye bye.